Swayam Prabha. Digital India. Educated India.
Starting going into the detailed designs that you have to consider for precast structures, for precast elements. And as we have said, as we have also listened this morning, a precast element and the precast structure undergoes some stages which we call a transient design stages or transient design situation, where it can behave in a different way because it works in a scenario which is different from what is the final when it's installed in the structure. And I like to show you this, it's quite an imaginative picture. This is a double thatched beam that you can use in an industrial building, in a shopping mall, in some kind of facilities like there. You can go up to spans which are more than 20, 25, 30 meters. And you can also appreciate here from that picture how thin also can be the webs, the flanges of this structure because of the use of high performance material, because of the use of pre-stressing. And then you have to transport to the site from where it has been constructed to the site. And the transport in itself is a process that you have to design. You can see there that you really have to check which are the roadways that you have to go through, because there can be radius of curvatures on that road, like this case, where your beam has to be handled with care. You see that you have here 2 tracks in this way, because what you do, you go to that curve and go leftwise with 1 track, and then the other track moves and you go right way in order to install that. As you can see, look here, the beam is basically constrained here and the beam is restrained here, okay? So if you think from a structural design perspective point of view, you can say, okay, but this beam is supported on one end on one of the tracks, is supported on the other end on the other tracks, and it's simply supported. Most likely is the same scheme that the beam will experience when it will be installed. It will be positioned on 2 columns. There will be some bars, some pins coming up. It will be connected, and you can consider that joint between the beam and the column like a hinged joint. But can you see here? You see that there is this, it's like a fork, okay, which embraces your beam. And what kind of constraint do you think, and why it has been done like that? What kind of stress state or loading scenario that beam can experience exactly when it's going to be transported and it has to be moved in a way like that? And so why the reason to have this fork which hosts the beam like this? Yeah, it's exactly. The issue is that when you curve, the beam will experience some kind of torsion, accompanied also by some, tilting effect, which tends to bend it in the minor stiffness axis. So you have to block also those deformations there in order for the beam to be stable. But that means that, okay, if you think of this beam in a classical portal, 2 columns, hinged connection beam, simply supported, you neglect torsion, you neglect the bending in the out of plane direction, because in most of the cases when you will have complete the building, this will not be governing this situation. When you are in this situation, is exactly torsion and lateral bending, which governs the design. So these specific situations have to be taken into account in the transient design situations. And this is the same beam, exactly the same beam, when you go to install it. When you suspend the beam, your beam is just hanged at 2 points, but it's free to move. And because of wind, it can, it's like a pendulum in the out-of-plane directions. These are specific situations that you only have during the transportation, erection, and handling. Because when you are installing the building, you can also see here, you see that here there are some elements which connect, and then you will use them to support also the roofs. These elements, you can also see their shadow on the other beams. Well, those elements then act like struts between the beams that prevent any movement in the out-of-plane direction. So when you are going to complete the building, this lateral deformation and torsion will be prevented, or at least can occur over a span which is much shorter than the wall span of the beam. So the most critical situation for this beam will be exactly, for this kind of structure, will be exactly during the transient design stages of transportation, handling, and erection. So when you have to design any of your structural element, any component of your structure for transient design situation, you have to consider, first of all, the casting. We will see when we will design a pre-stressed element that immediately after the casting and when you release the pre-stressing, there already is a design situation that you have to take into account. Then there is the demolding, the handling and lifting, storing. Handling and lifting, the first thing happens in the factory because you have to move from the precast yard to some storage yard and then wait for the transportation and so on. Storage, transportation, erection and installation. And when you go there, you have always to consider that there are the construction and erection tolerances. So you can see that this stage actually represents, I would say, 90% of the design of an element, because then there is just the final stage, which is the most classical one, the one for which you already have the tools from other engineering courses, engineering disciplines. But these are specific issues that you have to consider exactly when you have only precast structures. And these are some pictures you can see here. There is this moving crane and the concrete is flowing down, and there is this operator who is just assisting in moving. You can see that some fresh concrete has already been cast. You can see also here, and these are the reinforcement in the element. These are some other examples. These are tunnel segments that are finished in some way. But this is also to underline, when you cast, there is a very specific point that you have to take into account, which is the importance of the molds. So let's try to go for a very simple example. There is some very simple arithmetics to be done here. Okay, I have considered a column. Well, these sides may not be typical of precast structures because you can see it's just 3 meters tall. You can imagine it's for an apartment building, can be precast or can be cast in place. And it's 400 by 400 millimeter, it's square side, by 3 meter A. Okay, so if you calculate the volume of concrete that you need for this, it's about half a cubic meter. Okay, then if you are building in seismic region, nowadays most of the design codes, Euro code and so on, recommend the longitudinal reinforcement to be at least 1% of the concrete cross section. Well, for a 400 by 400, which is 1600 square centimeters, it's very easy because you have the Phi16. The Phi16 is 2 square centimeters, 8 Phi16 is just 16 square centimeters. It's just exactly the minimum that you need. Perfect. But then you have the stirrups. And the steel roofs, if you have a 400 by 400 and you are in a high seismic zone and you have to design for ductility, you must make the steel roof in this way. You must have an outer steel roof, but you also must have an inner one, which connects the central reinforcement. Because it's prescribed in the seismic design codes that you cannot leave bars which are not tied at more than 300 millimeter spacing. So if you do not tie this intermediate bar, you will have more than 300 because it's just a little bit more than. But okay, I made a simple calculation, and you use 8 millimeter steel roofs because, as a matter of fact, you don't find lower diameter bars in high ductility steel, which is the one that you require for seismic applications. Spaced at 75 millimeters in the critical regions, top and bottom of the column, and 15 centimeters elsewhere, which complies with the code. So if you work out the quantity of steel that you need in this column, it's about 55 kg. And just to have an idea, it's 55 kgs over about half a cubic meter of concrete. So it means that you have more or less 100 kilos per cubic meter of steel. This just to familiarize also with these numbers, which will help you also, in the practice to have some feeling, some immediate evaluation of what's going on. Well, then if you calculate the surface of the molds that you need in order to cast this concrete and you work it out, it's about 5.5 square meter, because you have to work out the perimeter, allowing for some overlapping somewhere, and work out for 3 meters. Well, this is also to show that there is some, strange way in our practice of computing the cost of the material, because we compute the concrete by cubic meter, the molds by square meters, and the steel by weight. So different units in the same element. But this is, what you need to cast this column. Well, prices may not be so updated, but these are some average prices of a few years ago in Italy. A good concrete is around 120, 125, 150 euros per cubic meter. So it's 65 euros of concrete for your column. I think 1 euro is 100 rupees, more or less, something like that. Yeah. So you can easily make the math. Steel, well, steel now has exploded on the market, but we can say that between 2 and 3 euros per kilo you can have it. So you see that 55 kilos of steel already cost more than twice your concrete. More than twice your concrete. When you will see next week fiber reinforced concrete, and everybody will claim, oh, it's more expensive than regular concrete. Yes, but consider that you already have fibers inside, and those fibers can help you in saving some of this steel. For example, in reducing some steel roofs. So there is a trade-off. We must be fair in the comparison. And then I checked the prices on handbooks, and molds are paid around 30 euros per square meters. 5.5 square meters is 165. So you can sum up and you say, okay, the materials, the total cost is about 370 euros. 55% of it is due to the materials. And you see the materials share about 2/3 the steel and 1/3 the concrete. The price of the steel, it's the steel already formed, already detailed. It's not bulk. It's already in the shape that you want. And 45% of the cost are the molds. That's something interesting. But there is a drawback in this reasoning. Well, you can say, well, I do not use the mold only for one column. If I have to make a multi-story building, and I have been, as a designer, wise to keep the cross-section of the column constant for at least 2-3 stories, that's true that if you go up, your safety factor is higher if you keep the column larger, and if you go lower, your safety factor is lower. But you have also to comply with practical things. If you change the size of your column at every floor because you want to have always the same very strict design, very strict safety factor, you will have the issue that molds cannot be reused in most cases. But you will also have complicated detailing when you have to, connect the reinforcement from the bottom floor to the top floor. Because either you bend it or you go for, cross-cutting and superposition and so on. So you have to take into account that probably that 5 centimeter more of concrete we have seen is actually the cheapest part of the game. It costs more probably to go into a complicated detailing. But if you have done in this way, and you can say, I will reuse my molds 3 times, then you can share that cost that we have seen at least by 3 and attribute to that. So in this case, the share of the cost is a little bit more reasonable, but still your molds account for 1/4 of the total cost of your structural element. This is for the simplest one. You have nothing else to do than cutting the molds in the sides and connect them with some special devices and so on. Nothing to do if you have to cut some complicated shapes. Well, why do you think it's hard to reuse the molds more than 3, maximum 4 times on a job site? What? Yeah, one thing is that because when you strip the molds, you can have something. So the quality of your finishing will not be good. And this is also because even if we use a timber, which is exactly mold timber, there will always be some infiltration of the slurry of cement inside that. So after a certain point, you cannot use that mold. This is also another important thing, because those molds are timber but cannot be burned because they contain cement, which is a toxic waste. So you have to dispose them with a special procedure. The other thing is that if you vibrate the concrete, and generally you vibrate the concrete in columns going from the top, or you vibrate at the mold, your timber molds tend to deform. So you will have columns, you risk to have columns which at a certain point they bulge a little bit and so on. So there is a limitation in reusing the molds. So this is just a very simple example to show you that, as yesterday morning it was also told to us, molds have to be designed. You cannot overlook them, because if you overlook them, for example, here you are overlooking 1/3 of your costs. And this is an important thing. So this is what I've already said. Well, when you go for precast structures, in most cases you use steel molds that are designed. It's a mechanical engineering design process to design them, so you can optimize this. And you can see here, for example, these are the molds that are used for precast tunnel segments that also undergo a special curing process in what it's called carousel. So it's really something which goes, like a carousel in the steam curing and so on. These are some other examples. They were these, flower tulip-shaped bridge piers, and some polystyrene was used. Well, polystyrene is easy, but it's also an environmental problem, because when you remove this, it can, you have these small spheres flowing through the air, and it's basically plastic that you are disposing. But this is the nice finishing effect that can be appreciated. This is an overpass in Idaho. Well, here you have, this is a caisson beam for a bridge. You see that it's not uncommon that if you have a 30-meter span bridge, the span to depth ratio is 15. 30-meter span means 2-meter deep beam. So people can stay inside. And this brings another important point. So imagine, as we were saying yesterday, imagine that you have to cast vertically concrete for 2 meters. Concrete is a fluid which weighs 2.4, 2.5 times more than water because its specific gravity is 2400 kilos per cubic meter. So if it's fluid, and when it's in the fluid state, and you have to consider it as a fluid, the hydrostatic pressure, can you imagine the pressure and the bending moment that a mold must resist in order to perform its job? So alternatives, well, nowadays that 3D printing has become popular. For example, this is a project that we did with a company. You see we had this, well, it's better I put it in. You had this robotic arm which printed this hollow tube. This was fiber reinforced, so the fibers were there to take the hoop stresses due to the hydrostatic pressure, and then we filled it. So this is an opportunity. It's not exactly what I will say the future of 3D printing, because you don't use 3D printing in concrete just to make the molds, but it's a possible application. So how do we design the formwork? There are guidelines. There is this report from ACI Committee 347, well, which actually states that you apply a model which is hydrostatic and then remains constant. Why this? Because as long as you, first of all, concrete is not a fluid. It's more like a granular material. But also in granular material, like granular soils, you have a pressure whose trend is hydrostatic and is related to the specific gravity, to the thrust coefficient. But concrete is a granular material whose characteristics evolve over time. So it is considered that as long as you cast, okay, and you rise up with your volume, the bottom part, the more you go up, the bottom part stays undisturbed. And when concrete stays undisturbed, and if you don't go to disturb it more, it starts, setting. And this reduces the pressure because a network forms and you do not need anymore, it does not belong anymore as a fluid. So this model works, but anyway, as you can see, for a concrete slump less than 175 millimeters. So it's, well, I don't know the Indian classification, but this could be what we in Europe have class S3. We have 5 classes. S5 is the maximum workable. Then you have SEC. 175 could be up to class S3, which is workable, but not very fluid. And a depth of casting less than this, or walls below 4.5 meter 8, and placement rates less than 2.5 meter per hour. So you must go slow in casting and allow the concrete to rest. Because if you go faster, your concrete has not enough time to, and also it's considering that the inertia of the concrete that you are casting can disturb a wider region. So you have this phenomenon which is called a thixotropy, that concrete, if at rest, starts flocculating and setting, but if you disturb it, you put it back into the fresh state. And you see this P maximum is calculated, well, as a function of the rate of placement. The slower you go, the lower is this P max. And of the concrete temperature, because we know that in colder temperature, concrete sets slower, and in higher temperature, concrete sets faster. Then you have a concrete weight coefficient and the concrete chemistry coefficient, which take into account, well, concrete weight, you can have lightweight, you can have heavyweight concrete, and so on. And concrete chemistry can also depend on the type of cement. For example, if you have a pozzolanic cement whose hydration is lower, you will have also a slower decay of the formwork pressure. Well, this has been, why this model? This has been calibrated through experiments. You see, this paper is quite old. It's more than 60 years old, but still, it's valid. And you see that you have this initial hydrostatic line, and depending on the speed of casting, on the casting rate, the slower you go, the earlier you stop your hydrostatic increase of the pressure, and you can go there after as a constant, whereas the faster you go, the the wider is the region, the deeper is the region into which you have to consider the hydrostatic pressure of the molds. And this is, I always like to put some, research content into these slides. Actually, this is a work which has been done by an IIT Madras alumnus who has been doing his PhD with me in Milano, and in 1 month from now is defending, so it's closing up. Some of you know him, Sriram Kompella. We did tensile and shear tests on fresh concrete. That was for 3D printing, because we wanted to understand, okay, how fast we can go with printing before the filament breaks, or how fast we can pile up the things. I think, well, I should give the PowerPoint, but there was a movie where you can see that, but there are movies. And you can see here, the early age strengths of this material as going from 100 minutes. You see, at 100 minutes, the behavior here is quasi-plastic, and then you start developing a typical brittle material for tensile test. And we also correlated, this time with the slump flow. As long as you go with time, the slump flow decreases, because it's what happens. These are other correlations. So we have cast with a well-designed formwork. We wait the right time that concrete gains enough strength to release the pre-stressing and so on, and to demold, and we demold. Okay, well, demolding, in some cases, it's a moment where before that the element is just resting more or less continuously on the precast testing bed. When you demold it, and you generally do it lifting it up through some lifting hooks, at that moment, immediately, you have the element subjected to its self-weight. So this is the reason for which in the codes, you also find that when you design for lifting, your self-weight must be amplified by a factor, generally 1.4. This factor is for dynamic amplification, because you have this sudden inertia effect. And these are some examples. You see, with these tunnel segments, you have this, device here, which actually creates vacuum. It creates a suction, and you can lift your segment, or you can have this. You can see here there are these lifting hooks, in a sense. Well, which are the stresses that we have to resist when we demold an element, and for which the element has to be designed? Well, there is a situation in which the element has already been demolded and it's there floating in the air, and we have said we design it for the self-weight, for the dead load amplified by a dynamic amplification factor. But the same act, the very act of demolding, what are you doing? What are we doing? Well, we are exerting, we are forcing the element to go through some shear stresses along the interface with the molds. And at the very onset of the demolding, the shear stresses are applied all along the surface of the element. So it's a very wide surface, and these shear stresses, which are due to friction, can be very high. So how can we guarantee that our structural element is fit for demolding, in a sense? Well, we have active and passive measures. Active measure, okay, we know that there are some shear stresses, the friction. We have to guarantee enough shear strength. But what is shear strength due to in concrete? Well, if you make the Mohr circle, this will be a case in which you only have, I don't know if I can write. Well, anyway, we are applying just shear stress. When we have only shear stress, the state of stress is equivalent to a principal tensile stress state, which is just rotated by 45 degrees. So you can easily correlate your shear stress to tensile stress. And so if you have to resist the shear stress, you need adequate tensile strength. But this is one thing. And the other thing is that we can have passive measures. First of all, we can use demolding agents which reduce the friction. And then we can use shapes of your structural elements and of your molds, which can ease the demolding. So first thing, if we want to guarantee an adequate, well, not only tensile strength, this is also done because you need to guarantee an adequate strength, also compressive for pre-stressing release, and because at 16 hours you have to lift your element and move it somewhere. In precast structures, generally we use heat or steam curing. The precast beds you will see in the factory, there are like roadways or runways which run for 100 meters. They are generally 2.5 meter wide, and in most cases there are some pipes inside where you have either steam or hot water going. At the end of the casting process, you cover your elements with some waterproofing covers, and the heating process starts. This is the diagram here is a typical curing process in a precast factory. You can see that you start at, 20 degrees is, hopefully the average time, but in summer, in a precast yard, you can go to 35 easily, whereas in winter, you can be around 10, 15, not less, because it's covered and some way heated. So you start here, you have a stabilization, then you start your ramp up. Generally, this is done, you see here in this case, this is a true process, so the numbers you can take it for granted. In 2 hours, we ramp it up 40 degrees, so it's 20 degrees per hour. It's, let's say, more or less half a degree per minute, a little bit more, 1.5 minutes. And then you have a period which can go from 8 hours in winter to 4 hours in summer, because in summer you already have the ambient temperature which is higher, in which you and checks and 28 days. You see here that we have other, dispersed points up to about 42 days. Well, this is due, for example, to summer closure. And you close it for summer, you didn't cast, but you also didn't test the specimen, so you have some specimens that were tested at 35 days and so on, depending on that. But still the population is good, because then you can calibrate a low, and you can see what does it happen. The red curve is what you find in the Eurocode or FIB model code as the aging curve of a normal strength concrete for normal curing. Is this exponential relationship, and we use a factor beta. This is related to the type of curing and in some way also to the type of concrete. This factor beta is taken equal to 0.25 in the case of normal cured concrete. With accelerated steam curing, you see, compared to the red curve, all our data points are higher. We have a faster strength gain in the early ages. What is the, drawback in a sense, but it's not that, is the fact that if you see, we have interpolated the data with this black curve with a good R-square correlation coefficient, 0.857, is that after 28 days, you have a less gain of strength. So you, in a sense, consumed already what you could do, or most of what you could have at the beginning, and you have less reserve. Well, this also depends on the type of cement. This was based, this data base was calibrated. This was a SM2 used in the factory, which is cement with limestone filler. Generally, it's up to 30% limestone filler. But if you have pozzolanic cements, slag cements, they continue to hydrate these curve shifts. But what is important to remember is that you have a faster strength gain, so you have to calibrate your strength gain curve according to this model. The other issue is that, so this is the active measure. How do we get higher with strength when we need it at early ages? Passive measures, we have said that you can use demolding agents. And, well, it's not a widely researched topic because it's mostly then related to technology, but as an important outcome on the aesthetics of the concrete. And you have to think that in most cases, well, I will say in 100% of the cases, more or less, your precast concrete will be visible, will be a facade concrete. So the aesthetics is very, very important. And if you have this stripping, spots on your concrete, well, your aesthetic will not be so nice. We worked for a project with a famous architect. He wanted white concrete, and he wanted gloss finishing. So that we had to work with the mold. It has to be still polished in some way. We had to use demolding agent and so on. So this is very important. Well, in that case, the strength was not an issue. We had plenty of strength, and the element was just a facade shell. So nothing else to support itself, being supported by a frame behind it. But the aesthetic was the most important requisite. So we have also to consider this. We are structural engineers. We like to deal with calculations, with tests and so on, but sometimes aesthetics, especially in precast, is very important. And you see this, you can find it. I put the paper, it's about 10 years old, but you can find it on the web. And this paper, they measured the addition energy. You see here, the blue is a new formwork surface. The red is used formwork surface. Well, obviously, if you use the formwork, the addition diminishes. And polished formwork surface. And they also use different kind of demolding agents with some additions. You can see here you have one mineral base with different solvents and acidifier, or a pine ester with different solvents and acidifier. So this is also to show you, in some cases, if you work in a factory, you have a specific requisite, you can make some preliminary tests. You just cast a tile, there is no need to cast a wall element. You can make some push-off test, or you can make some strip test and just validate what is your choice, for example, of the demolding agent. And here you can see a new versus a used formwork, which can be the aesthetics problem. If your customer asked you some specific aesthetic requisites and you give him this, he will simply send it back to you and you won't get paid. That is the most immediate outcome that you can get. Okay, we have stripped, now we are lifting it. And here it seems to be, okay, there is some technology into it, but there are also some exquisite structural design issues. Because you see, when you lift an element like this, this element there, it's suspended there. So you have that, beam-like part, which is going to be subjected to moment. And you have to design for that. And likely, when this element, this is something for underpass. So when it will work, it will have earth restraining this, outgoing deformation of the supports. Here, there is nothing to restrain that outgoing deformation. So this is a scheme in which the element will work differently than before. You see, this is a demolding of a hollow core slab, which is really forklifted with these doors. This is a column, which is lifted with these vacuum systems. And these are some schemes that we use. For example, if you are lifting a slab, you always tend to have 4 lifting points, so you distribute the loads. And why, for example, let's focus on the slab. Why, for example, would you prefer this lifting system or even this dual bending? Yeah, because you see, when you have this one, the force that your lifting rope is applying is inclined. That inclined force has a vertical component which equilibrates the self-weight, but has also a horizontal component. Well, it's true that those horizontal components are self-equilibrated. But locally, what do? They apply a compression force at the extrudos of the slab. A compression force at the extrudos of the slab means an additional positive bending, an additional bending moment which sums up to the one due to the self-weight. So you are inducing additional lifting actions, and well, you might have well, it's difficult that your element will not resist. There have been cases where your reinforcement was designed so strictly that it was not enough, considering also the overweight. But you might have premature cracking. If your element starts cracking and the crack width is already too wide, already in this stage, you will never recover it. So your element, and you can have some deformation, and consider that if it's cracked, then there is the interaction with creep. You can have your element going into service, which is already some permanent sagging. So there will be some functionality requirements that then probably will be reflected in the fact that if you have to apply some waterproofing, you will have an imperfect waterproofing, or if you will have to apply some additional casting, you know, half a centimeter of camber, of sagging for 100 of square meters of surface means that you have additional concrete to pour and to level that you have not accounted for. So these are all issues that you have to take into account. And these, you know, let's say parasite forces which arise due to bending are even more evident here. Here you have this force, and you have a compression force just at the top, which causes you to have additional bending moment. This just to show you that the you know, lifting has to be designed. Has to be designed not only for the equipment and so on. This angle here has to be designed. You have then to calculate the action and check your structural element for those specific actions. And here are some examples. For example, there is this hollow core slab here, which has some, you know, place here for ducts and so on. Well, if you lift with this system here, you are forcing the element to, you know, bend in this way. Generally, in hollow core slabs, the transverse reinforcement is non-existent or very, very limited. For this reason, these are elements where fiber reinforced concrete works very well, because the fibers help you in, you know, mitigating these effects. But this way for this element is exactly a wrong way of, I have never seen, well, in practical experience, I have never seen, because they are an obstacle to the, because hollow core slabs, you know, how are they made? There is this, you know, they are the grandfather of 3D printing in a sense, because you deposit a very stiff concrete and at the same time you apply this vibration. So it's just longitudinal reinforcement so that it can go. Then you can have something at the edges for detailing, but never that. So extruders cannot move, yeah. So that, yeah. So really, this is the case where you do not have any provision to resist this incorrect way of lifting. And the same is for this, you know, channel. If you lift in such a way that you have this bending, you will have some cracks. Imagine that if this is an element which has to be waterproof in some way, well, you see, but the water will be here, yes, but here there will be ground and so on, and if the, you know, moisture from the ground with all the, generally in the soil you can have sulfates. It's the most common aggressive agent that you can have. You can have early problems of durability. You have designed it for a certain service life, but after 5 years you will start seeing everything leaking through this canal. So these are important aspects where you require careful structural design, because this can compromise not your safety, I will say. Well, in this case, the element can also break, but surely compromise or your functionality or your serviceability or your durability. Well, another important thing is, as I said yesterday, the advantage that we have in precast construction is that we cast elements horizontally. And horizontal casting guarantees a better quality control. Even if you have to cast a slab, which has to serve as a wall, for example, for a small tank or a reservoir, it's better to cast it horizontally and then lift it up. But when you lift it up, care has to be done, because you see, you make, for example, with this scheme, never use a single hanging point, because this will risk you to underbalance your element. Because if you have a single hanging point, when you lift your element here, you will have the force here and the other reaction force will be here. that if you can balance, it's better. But the reaction force at the pinning point, you have to consider that that equates, largest part of the weight of the element on a single point. The corner is a single point. So you will have a concentrated force, which risks you to break locally the concrete. Nothing troubling from the structural point of view. But when you go to your job site, to your customer, and you bring him a column which is already chipped, what do you expect from him? What the functionality? Because then the building must be finished. There will be some other elements it has to interact for. So these local damages will disrupt also the continuing erection process, because if you have then take care of these local repairs, your schedule will be disrupted because you have to interrupt and you have to go there with another crew that goes this repair and so on. So this is something which is important also from the project management point of view. And here you probably will see something in the factory visit. These are some images of lifting. And this is another example. We will have a dedicated lecture on precast segments. But you see this, I was discussing yesterday, the tunnel ring, when it's completed, is a closed ring and it works mainly in compression. But when you use precast segments and you lift them up, typically at 2 lifting points, what do you have? You have that the outer parts of the segment will behave like cantilevers. So this is a completely different way for the element to work, because when it's completed, it will be in a ring and will be just subjected to compressive forces. Here you will have a bending moment and the negative bending moment for the cantilever. Typically, when we store the elements in a part of the factory and so on, we do not support them at the very edges like they will be in the structure. But we put the supports a little bit inside for the sake of simplicity of handling and so on. And also because in this way you can better accommodate some tolerances, because imagine you put exactly at the edges. But what does that mean? It means that if you have the self-weight, your diagram of bending moment will be exactly as it's shown there. Well, I saw in the diagrams you showed this morning that you draw the moment with the opposite way that you do. Well, we draw the moment on the side of the stretched fibers, but that is. But this element here, you see, is going to experience here some negative bending moments. Most of the cases, your reinforcement is always on the top, or at least you have to put on the bottom, sorry. You have to put something on the top to avoid excessive cracking. As we will see, it will be the day after tomorrow when we will see the design of pre-stressing. Well, generally, these support here, they are, for example, 20 centimeters from the edge. They are not really in the middle. But they are at a distance where if your element is pre-stressed, at that stage, at that position there, the pre-stressing is not yet fully developed, because for developing the pre-stressing, you need the development length. Okay. At that distance there, your pre-stressing is not fully developed. So you risk not to be fully covered there. Also, consider that, well, this moment will be exactly the same sign of the pre-stressing, so it will sum up to that. So that is another structural design issue that we have to take into account when we design for this situation. And the other thing is that you have to be careful, that if you pile up your elements more than one, your supports must be in line or with a minimum tolerance, because otherwise what do you risk? You risk that the element above transfer the forces to the element below, but does not go to the support, goes to the element. So you risk to have a situation which is this one that we have shown before, but with another concentrated force, which is the reaction which comes from the element above. So this also has to be taken into account. And this is, for example, a picture of how these tunnel segments are stored. Well, in this case, this is also a typical situation because you store them and you transport them in such a way, in this case, 5 larger elements plus the smaller one. The smaller one is the key. This is what you need to complete a ring. So you transport in one pallet all what you need to complete a ring. And this is also what happens, in tunneling in most cases, especially if you are in urban areas, but also if you are in highway tunnel or railway tunnel, you have this TBM machine. Have you seen somewhere on YouTube or on, some website of companies working on this? You have used it for the metro, yeah, for the metro. So the TBM machine excavates, but there is a long, the part which excavates is just the tip of the problem. There is then a retinue after that, and there is a train, and also there is a part which transports these segments from a stocking yard, which is nearby, just to the tip of the tunnel boring machine. And it's good to have all one segment transported in one carriage so that you have all the elements to complete your ring, because on that ring then when the TBM advances, that gives back the thrust to the TBM to advance. So this is also for rational, I will not say faster, but I will say rational execution of the excavation. Some examples here, well, in some cases when you go for transportation, you must have an expert of the roadway code, which dictates which are the maximum size of the vehicles and so on. In some cases, it's not infrequent to find on the highways, especially when you have to transport some large precast structures. Well, you have a special transport, which means that you have the police before and then after, which keeps, at least warns and keeps the traffic slow in the vicinity. There are limitations about the number of elements that you can transport and the maximum inclination that you can give to them, the way that you have to support them, and so on. These are some images which are taken from our circulation code in order to deal with this. And these are some examples you see in this case here. In this case here, what radius of curvature had to do that beam? Yeah. Well, in Italy and in Europe, it's the road circulation code. It's the road circulation code, which restricts the width, the width of the cumulative, so truck plus what you are transporting. I think that you can exceed a little bit the width of the carriage, but not much more than that. So you have to allow at least for the passage of one car through half the carriage plus the emergency road. But in that case is the case where you have a limited speed and you have the police beforehand and after that keeps the speed and serves also as a warning for the for the other cars and vehicles in the back of the queue. Okay, and these are elements. This is the same picture that I showed you beforehand, and this is also, yeah, you can see here. These are two beams. These are basically bridge girders. You can also see, appreciating here, that there are some stirrups going up. You install here the slabs to finish your highway or your roadway. And you see here this, transportation fork that just provides those restraints against torsion and lateral bending that we were discussing before. Other information about, for example, you have to, allow some movement, because otherwise, if your constraints are fixed, you induce some additional restraint forces to your element that is not designed for. This is some erection. You see, this is a complete facade which is lifted. You can see also here some kind of, I will not say complication, but it's, something that has to, distribute also the lifting forces that you have to deal with. And in some cases, for example, if your column is very, very tall and slender, you can use some temporary supports which also help you to keep it in position. Because the other issue, as we have seen yesterday and also in some slides this morning, there were some examples of slab foundation elements which so if you have a continuous foundation or a slab foundation with reinforcement which protrudes outside and you have to fix the column there will be a moment in which the column stays there, but it's not fixed in any way. And you hardly can rely upon the safety that a lifting hook can provide, because the lifting hook puts the column in position, but then you have to keep it fixed and guarantee some verticality in order to tie or realize the connections. And these are some examples. You can adjust these struts to the required thing. Other examples of erection, as you can see here, this is the crane which is moving the beam to this, very long, as you can appreciate, building, industrial building for precast elements. Well, now, what time is it? No, half an hour, okay. No, okay, so we can go, but now I need some maths. So it's a little bit, so we do with some maths now. Okay, so this is the specific situation in which you have to lift and, install the beam. The failure mode which can happen in that case and against which you have to design and guarantee your safety is called lateral torsional buckling. Because at the same time, you have the main flexural action due to the gravity loads, but you have also flexural action in the out of the plane direction, which is, as a matter of fact, the worst one, because it's the direction in which the beam is weaker from the flexural point of view. Because if you have, like here, you see this beam here, imagine that this is B and this is H. The stiffness against gravity loads is BH cubed divided by 12. But the stiffness in the other direction is HB cubed. So if this is 20 centimeters and this is 2 meters, it means that the stiffness is 20 by 2 meters, 0.2 by 2 to the cube in one case. In the other case is 2 by 0.2 to the cube. So between the two stiffnesses, if you work out the math, there is a 100 factor. So the stiffness in the out of plane direction is 100 times less than the stiffness in the main direction. So it means that you can easily, if there is nothing which blocks you and you have just a slight imperfection, the beam will immediately, bend in that direction. But this bending, in order to accommodate the compatibility of the deformation, cannot occur as a bending alone, because there is also the gravity load, the self-weight is already there. So it has to bend and deflect downward. This can occur only if you also allow some torsion. So that is the reason for which we call it lateral torsional buckling. How do we approach the problem? This is the reason for which I say I need some math. Well, in this way, we have to approach problem, first of all, in 3 dimensions. And I was not a very good student at drawing. When I was a student, we used it to make hand drawing. Then CAD appeared. We make this fancy course of CAD as an addition to our hand drawing class. So, not very good at drawing, not in 3 dimensions. You make the 3 horizontal Cartesian projections. So this is the main view of the beam, okay? The main span, you see that. It's a very long and tall beam, but very thin in the web. And we call X the longitudinal axis. We call Y the vertical axis, which is point downward, because the gravity loads point downward, so we have gravity loads with sign plus. And then you know the right-hand rule. You have the thumb with the x-axis, the index is the y-axis, the middle finger gives you the direction of the z-axis. So the z-axis is pointing inward. If I look from this side here, I see the cross-section of the beam with the y-axis and the z-axis going left, because I'm looking this side. And the x-axis is going this way. And if I look from the top, I see the x-axis here, the z-axis going side, and the y-axis is going downward, so I don't see it. It's pointing down. Okay? Is that clear? Whenever you have to deal with a structural mechanics problem, the first thing is to set a reference system, because from that onward, everything will depend. This is what I always tell my students when I ask a question at the exam and they immediately write the equation. And I say, okay, that equation as it's written, in which reference system is valid? Because if you change the reference system, it's not that the equation changes, but the signs may change. Okay. Now, this is a buckling problem. And buckling problems, you know, they were mathematically formulated correctly by Euler about 300 years ago. Euler was one of the greatest mathematicians of all the history, but he had a, you know, some kind of nice fancy. He discovered buckling by imagining, by hypothesizing some absurd mode of deformation to occur, and then he looked for the conditions for this deformation to occur. And you can prove that this only by mathematics. Well, evidence there was. The buckling of a thin column was there. But if you consider that the column is compressed and you only apply desenvenant, you say the compressed column just shortens, cannot bend outward. Euler hypothesized this. So what does this mean? It means that you have to hypothesize a deformation mode for your structural element. And then, you know, in structural mechanics, we always rely upon a principle, and we implicitly rely upon it, and sometimes we forget. This principle is the principle of small and negligible displacements and deformations. That is at the basic of any structural mechanics theory. We assume that there is a structural element under certain loads, and that element deforms. But we assume that the deformations, first of all, are small. What does it mean, small? It means that compared to the dimension of the elements, they are one or several order of magnitude lower. The other important, and this is okay, this we always keep, because otherwise we will not be able to use our elements. When you design a slab, you check that the deflection is less than 1/200 the span. Otherwise, I joke, if I throw here an apple, the apple will go in the middle of the room. But before this, or your tile will jump up, your walls will crack, and so on. But the other part of that assumption, we say the deformations and the displacements are small and negligible. The second part is the most important one, because the fact that they are negligible means that whenever we work out our models, we do not consider the beam or the column or the elements deformed. We simply work with them as rigid and undeformed. When you have a beam and you calculate the vertical, the support reactions, you don't consider that beam sags, consider straight. That is the most important part. We will dedicate 2 classes next week to that. Because when you deal with buckling, you must make an effort and you must say, okay, that part of the assumption does not work anymore. I have to accept that my deformations are no longer negligible. And in the slides that Professor showed this morning, with respect to earthquake design, one of the failure modes was exactly because there was no compatibility of the deformation between the lateral system and the gravity loads. If you deform laterally too much, you have that your gravity load, your column will do like this, and your gravity load continue to be here, and at a certain point, it fall down because of this. So it's extremely important in precast structures, also because precast structures are more slender. We have said yesterday, you have larger spans, you have taller columns because you have better materials and better quality control. But more slender elements means also more deformable. So this deformation cannot be any longer negligible. So what we have to do is that instead of writing our equilibrium equations, okay, considering the undeformed beam, we must write considering the deformed beam. So you see, this is the main axis of the beam, and the beam deflects of a certain quantity v, function of x. Then you also have the lateral deformation. If you look at the beam from the top, you will see that in the out of the plane direction, the beam is going this way. So besides the main deflection v, you also have another deflection in the out of plane direction, which I call a w. And I put the minus sign. Why? May I will be back in a moment to my place. Why did I put the minus sign here? Because the axis, the z-axis, positive direction, is going that way. And so that displacement is going in the opposite way. So for this reason, I put the minus sign. And then if you look at the cross-section, the cross-section is rotating. So you start from a straight configuration, and then your cross-section, you know, why it has to be like this? Because it has at the same time to deflect downward and to deflect outward. So in order to accommodate both the flexural deformations, it has also to rotate. And it rotates of an angle phi. Okay? All these quantities, the deflection v, the deflection w, and the rotation phi, they are a function of the coordinate x. So they change along the axis of your beam. There is a point where there are the supports, the restraints, they are 0. And as long as you go towards the mid-span, where generally they are maximum, they will increase. But what does it happen? The external load is always only the gravity loads. And the gravity loads continues to be vertical, no matter that the beam has rotated a little bit. In our reference system, it's always vertical. It's true that we live on a sphere, but the radius of the Earth is so large that we consider it continuously vertical. So we have changed the reference system, which was x, y, z, is moving with the beam, but the load is not moving. So if you have a gravity load, you have a bending moment like this. You see, okay. Gravity load gives you this bending moment. And this bending moment, how do you visualize it? I don't know if you are familiar with this notation, the double arrow vector. This is a moment, and the rule is that if you put your thumb in the same direction of the double arrow, the other fingers of your right hand will give you the rotation sense of the bending moment. So actually, here, this is the bending moment due to the gravity loads. In the original system, undeformed system, you have y and z. This bending moment is only along z. But then the beam cross-section has rotated, so your axes are no longer y and z, are y prime and z prime. But the bending moment remains the same because the load at least this is in structural mechanics, the load do not follow the beam. If you go into aeronautical engineering and you have to design the wings of a plane, in that case you have a follower force, because the force is due to the aerodynamic interaction with between the wing and the air, and it follows the deformed configuration, also the force. But at least in this part of civil engineering, we are lucky. If you have to design a wind tower, then will be a little bit different. But in this part, we are lucky. The force does not follow the deformation of the beam. But what does this mean? It means that in the YZ system of axis, your bending moment had only a component along Z. But if you change your reference system and you have to remove the fact that that rotation is negligible, because if you say that that rotation is negligible, nothing happens. But you exactly are stating that rotation is no longer negligible. So my bending moment M, which is this blue arrow here, when the beam rotates, will acquire a component normal to the cross-section, which continues to bend it into the main plane. But will also acquire another component which bends it in the lower stiffness direction. The other fact is that if you look it, not from this point of view, but if you look it from the top, this is X, this is Z, your bending moment is this blue one here. This bending moment acquires component like this, but also acquires a component along the axial direction. That is torsion. So a bending moment which originally was just causing flexural action in the main stiffness plane, as long as the beam just starts, you just need a little bit. This is also the reason for which we call imperfection sensibility. You just need the minimum tolerance that you already have all the three of them. So we need to do a little bit of trigonometry. So you see, let's look at this picture here of the cross-section, it's easier. The bending moment M is this one. Originally, it was along the Z-axis. Now we want to calculate its component along the Z prime axis. So we have to project this bending moment here along this direction. We have to multiply by the cosinus of this angle. And as a matter of fact, if you look at the similitude of the triangles, if the rotation angle is phi, that angle is exactly phi. So the moment along Z prime will be M times the cosinus of phi. But here comes the first part of the assumption that we said. The displacements, deformations, the rotation, it's true that are no longer negligible, but remains small. So if phi is small, its cosinus is more or less 1. This is an important outcome, because mz is the moment due to the self-weight. So is the principal, static regime for the beam. The principal static regime does not change, as a matter of fact, so it continues to work as before. But together with it, the lateral torsional regime appear. So, for example, this moment here, the moment along y prime, this one here. Well, if the previous one was m cos phi, this is m sin phi. But phi is small, so you can say that the sinus of a small angle is more or less equal to the angle itself. Because we like trigonometry, but as civil engineers, if we can get rid of them, sinus and cosinus is better. So we use quite much asymptotic formulation. The cosinus is 1 and the sinus is the angle. In radians, yeah. And then we have the torsional moment, mx prime. You see that x prime is going in this direction. The moment is going in the other direction, so you have to put a minus. M, and is the sinus of this angle. And this angle is the rotation angle, so it's the first derivative of the deflection in that direction. So actually, what we have done here is to decompose the moment, which in the undeformed reference system was just m along z equal to m. We have decomposed it along the new axis of the reference system, x prime, y prime, z prime. And we have components along the three of them. Minus mw prime for the torsional moment, m phi for the lateral bending, m for the vertical bending. What do we do with this now? Well, we use the fundamental equation of the beam mechanics, and we know that the second derivative of the deflection is equal to minus the bending moment divided by the related stiffness. The second derivative is approximately the curvature. So in a sense, this equation is what we can call the constitutive equation of the beam, because it links a static quantity, the moment, we say force, to a deformation quantity, the curvature, through a stiffness. This is what we call the upscaling of sigma equal to E epsilon, which is the Hooke's law, the constitutive equation for a material point. This is the upscaling to the beam level, and includes all the assumptions that we make on the Euler-Bernoulli beam. But in the new reference system, mz prime, if I go back, mz prime is once more m. So this equation here, which is the principal bending, either if you write in the undeformed reference system or if you write in the deformed one, does not change. Because it's true that the deformations are no longer negligible, but it's also true that they continue to be small. Consider that, for example, if you go for aerospace engineering or spatial mechanics, you cannot consider any longer the deformation to be small at all. So you go into large strain theories and so on. But we are lucky, it's not for many cases, civil engineering is not for that. Let's go, what does it happen with other? Because we can write similar equations also for the lateral bending and for the torsion. For lateral bending, as you see, we had the deflection, which is this W here, but there is a change in the sign, because the reference system makes in such a way that we put minus W in that way. So when you have a positive curvature, you have also a positive bending moment here. Simply, you also have to take care that here you have Y, the moment of inertia ZZ, which is BH cubed divided by 12. Here you have the other moment of inertia, HB cubed, because you are bending your beam in the other direction. So these two moments of inertia are different quantities. But we have here my prime, and y prime is written here, is m phi. So put it and replace it. And this is the torsion equation, which correlates the derivative of the rotation angle to the torsion moment divided by the torsional stiffness. This G is the shear modulus of elasticity. For isotropic material is E divided by 2, 1 plus N. And JT is the polar moment of inertia. It's like if you pick up this rectangle and compute the moment of inertia with respect to an axis, which goes this way. The other two moments you compute with respect to axes which are in the plane of your rectangle. Oops, sorry. mx prime is equal to minus m w prime, and this is what is written here. So we have three equations. What do we realize? That the first one is independent. The main flexural action was there and remains there. The other two are related to each other. We have said, if you want to bend the beam in the out of plane direction, you also have to accept that its cross section rotates. And this you see because the two equations have common terms in common. But what we can do, you see, in the third equation, what do we have? We have the first derivative of phi, and we have the first derivative of w. In this equation here, we have the second derivative of w. So just calculate the derivative of both members of the third equation and replace the second derivative of w into here. So if you derivate once this equation, then you will have the second derivative of w here. But the second derivative of w is this one. So you put this into here, and you get the second derivative of phi plus m squared. One m comes from here, the other one comes from here. gjt, which comes from here, ejyy, which comes from here, times phi. And this is an Euler differential equation. Very easy to be solved, because if you call alpha m divided by the square root of gjt eyy, so basically this term here is alpha square, you have an equation which is second derivative plus alpha square phi equal to 0, and the solution is a linear combination of sinus and cosinus. Then this solution has two non-determinate quantities, A and B, that we have to calculate imposing the boundary conditions. What do we know? We know that at the support x equal to 0, the rotation is 0, because you see here we put a support like this. It's a flexural support, but it restrains all the deformation, vertical, horizontal, and rotation. So here, in x equal to 0, the rotation is 0. And if I put x equal to 0, what do I get? A times the sinus of 0, the sinus of 0 is 0, plus b times the cosinus of 0, the cosinus of 0 is 1. I get b. B has to be equal to 0. Good. Then I have the other boundary condition at the other edge of the beam, the other support, x equal to L. So in x equal to L, the rotation also has to be 0. But if I put x equal to L, and I already consider that b is 0, so this is not here, I have A sinus of alpha L equal to 0. I have two options. A is a number, sinus of alpha L is another number. The product of these two numbers has to be 0. The only possibility is that either one or the other is 0. But if I put A equal to 0, it means that phi is identically equal to 0. So there is no flexural rotation. So poor Euler. He didn't found any condition for which is intricate deformation could occur. This is what we call the trivial solution, but it's not what we are looking for. There is another possibility, that the sinus of alpha L is equal to 0. And trigonometric functions have these nice properties that they are periodic. They are 0 when the argument is 0. If you put alpha L equal to 0, either L is equal to 0, but a beam with 0 length does not exist. Or alpha equal to 0 means m equal to 0. Well, there is no moment, the beam is unloaded, nothing happens. Or it's infinite stiffness, but if it's infinite stiffness, the beam doesn't deform. So alpha L equal to 0 is meaningless. The other possibility is that alpha L is equal to pi. And if you work out alpha equal to pi L, you find what is the critical moment. Yes. So you have your self-weight moment, which is, well, the moment due to the self-weight is parabolic. The maximum is PL squared by 8. So you take an equivalent moment in this case, which could be, for example, the moment which has the same area, so 2/3 of the maximum, basically. And you compare to the critical moment. So you don't want your self-weight to be too close to the critical moment. And the critical moment, as you can see here, does not depend on the load, because pi is a number. L is the length of the beam. The longer the span, the lower the critical moment. You can imagine, the longer the span, the more flexible is the beam. And then depends on the modulus of elasticity of the material and on the stiffness of the cross-section. So the critical moment does not depend on the load. Depends on the boundary conditions, because the boundary conditions allowed us to arrive here, and depends on the stiffness of the cross-section. So the only way to increase your critical moment is, or you make your cross-section stiffer. What does it mean? Use a stiffer material. For concrete, it can be done, because the strength, if you increase the strength, you increase also the stiffness. Not proportionally. The stiffness goes with the cubic root, or the square root, more or less, of the strength. As a matter of fact, a C30 concrete has a modulus of elasticity of about 30,000 megapascal. But if you go for a C100 concrete, you have more than triple the strength, but the modulus of elasticity is 42, 45. So your modulus of elasticity is just 50% higher. This is an issue when we design high-rise buildings or high wind towers. The problem is not the strength. The problem is the stiffness. So one major trend is, can we in some way, it's a topic, there are some work, I think Professor Shah did some work with nano materials, to decouple the strength and the stiffness. Because in some cases, to have 50 gigapascal stiffness, I need 200 megapascal concrete, but I don't want those 200 megapascal because I'm not using them. So I want to, unlock this, but so far, just some attempts have been done, but not that. There is another way in which I can increase the critical moment and so shift further the crisis, the failure, to reduce the span. But then you can ask me, okay, but the span of your beam is dictated by some functional requirements. If your factory has to house some kind of machinery, you need a certain span. But then we go back to transient versus permanent design situation. You see, when you transport it, the span is this one. When you put in position on these columns, the span is still the largest one. So that is the most critical moment. But when you have completed your roof, or you have completed your roofing, you see these elements here. Those elements, for the lateral and torsional buckling, they act as support. So when you have at least started installing your roof structure, the span is no longer this one. The free span is this one. So you go from 30 meters to 1 meter, and the span is at the denominator. So it's inversely proportional. So this is the reason for which in the transient design situation, the failure is really likely to happen. And really, believe me, I was not witnessing this case, but my father, who was an engineer working on highways, reported me that in the 60s, when they installed viaduct beams, there were severe safety measures. There were the sirens, always active to keep the people out, because it happened, and you can imagine you have a 30-meter beam, pre-stressed, you release an immense amount of energy, and also the debris. You can have chunks of concrete which are shot at several tens of kilometers per hour because of this explosion. And if you are not in a shelter, it hits you and it kills you. So it's a failure from the structural point of view, okay? But the consequence is not only the loss of a beam, okay? It's economic loss, the delay, and so on, can also be serious. So this is an extremely delicate situation that you have to take care of. And this formula here, let's try. This formula here is very, very simple. So this formula here is very simple. And you can, immediately have an idea, because if you have for precast, as we said yesterday, you have standardized shapes and dimension. You can go to the website of the precaster and you find the beam shapes and dimension that you have. You can already have an idea, and you can make a very simple assessment, which is the span range I can go into for this. So before we have considered this cross section for the beam, am I right? And actually we had this reference system here, correct? And what I wrote was JZZ cubed by 12, and JYY was B cube H by 12. Okay? Then if you look at the equations that we used and we derived in the previous part of the lecture, there was also this quantity, JT, which I said is the moment of inertia with respect to an axis pointing inward for the plane. And if the cross section is such that H is much larger than B, you can work out JT as B cubed H by 3. So help me in reminding what we had as the critical moment was pi over L, you have on your slide, and I think was E, JYY, G, JT. Am I right? So, put this here and put this here. What do you get? You get pi over L. Then you can also remember that G is equal to E divided by Q1 plus N. This is from solid mechanics. So we make a big square root, and we have E, but G has another E inside, so this is E squared divided by 2, 1 plus N. Then you have JYY, which is this, is B cubed H by 12 times B cubed H by 3, which means that your M critical is equal to pi E, because E squared you bring out of the square root of B. Then you have here the square root of 2, 1 plus N, divided by 2, 1 plus N, And then you see you have b square h, b cube h, b cube h, but you have to extract the square root, so you bring outside b cube h. 12 by 3 is 36, and the square root of 36 is 6. So this is the same relationship as above, exactly the same relationship as above, but just, yeah, there is an L somewhere, you are right, here. I think that there is everything, yes, yeah. Now, okay, how do we change page here? No. Okay. Now, try to reason with me. This is the same cross-section that we have considered before. And imagine that this cross-section, as a matter of fact, this cross-section belongs to a beam. This is the axis of the beam. And you have the torsion moment as above. So it's this one, okay? This is the torsion moment T. And we have said before, and it was because of the solid mechanics theory, that this torsion moment is linked to the rotation angle by that equation. This you have from your, sorry, one moment, from your solid mechanics handbook. Okay? But as a matter of fact, in precast beams, you might have a cross-section like this. It's not a rectangle. Cross-section of precast beams can be like this, which are very similar. So this could be precast concrete. They are very similar to steel beams. Steel beams are like this. So what is the difference here? Well, the difference is that, you know, the beam, the rectangular cross-section beam, is, I will say, not a wise structural element. Because you have the beam, simply supported, gravity load, the maximum bending moment is only one cross-section. And bending moment means that you have maximum stress compressive on the top, maximum tensile stress on the bottom, but there is the central part of the beam which is less stressed. So these shapes here that we can use in precast concrete or in steel are just a way to optimize the distribution of the material. You put the material where is needed. You put the material here for the compression force, and you put the material here for the tension force. So you carry the bending moment through two normal forces and an internal lever arm. So we call this two parts, I write it here, we call them flanges. And what is this central part which we call the web? What is the purpose of that? Well, it carries shear, but it also guarantees that the two flanges work together, because if the two flanges are not connected, you cannot exploit this bending action. Well, as a matter of fact, for example, if you pick up typical steel beam geometries, the web carries about 90% of the shear, even more. And the two flanges carry around 85% of the bending moment. So in most cases, we simply say, okay, the flanges carry the bending moment and the web carries the shear, total of them. Well, this is a way to optimize, but there is another thing. Imagine that this same cross-section okay, let's try to draw it in a little like 3D. And here is the axis of the beam. And there is always this torsion moment here, T. Let's try to go back to the solid mechanics. If we have a solid, okay, and we apply torsion at both ends, equal and opposite for equilibrium, what does it happen? Well, surely it happens that if this is the original position of the cross-section, the cross-section, as we have seen before, rotates by an angle phi. If you pick up something and try to apply torsion, you have that the end phases, they rotate to each other. But we know from solid mechanics that when we apply torsion to a prism, for example, something else happens. Yeah, the cross-section warps. What does warping mean? It means that it tends to bulge out of its own plane. Okay, it warps, it warps. But imagine that you have a beam, the beam that we have seen before, the real beam, which comes on the track with two forks like this. Okay? The cross-section at the forks cannot rotate because the forks forbids them from doing that. But they can freely warp because they are not constrained outside of the plane. But in the beam, there is one cross-section which can never warp. In that beam, which one is? The midspan. Because the midspan is a symmetry cross-section, and actually that cross-section doesn't know whether to warp leftward or rightward. So in this uncertainty, it will not warp. Well, but if you have something, imagine that this is your cross-section. This cross-section will like to do something like this, warping. It cannot do. It has to remain like this. There is a stress state, let's call it a parasite stress state, which arises on this cross-section because of the restrained warping. And this stress state is a normal stress state. So even if you have torsion, and we know from the solid mechanics that torsion gives rise to shear stresses, if the warping, or where the warping is restrained, you also have normal stresses. Well, as a matter of fact, if you have, let's see, it can go back probably. Yeah, if you have a cross section like this one, like the, no, okay, the rectangular one, this one. Well, these normal stresses are there. But in the case of a cross section like this one here, the warping is rather complex. Imagine that you have, no, let's put it like this, black. To simulate the restrained warping, imagine that here your beam is fully fixed, okay? This cross section here will warp in such a way that it will tend to go inward. Imagine that that is constrained in the wall. It will tend to push on that side, and it will tend to detach from the wall on the other side. But it cannot do. So if I look from the top, here the beam will tend to push into the wall. To prevent it from doing so, I must have some compressive stresses like this. And on the other side, the beam will tend to detach from the wall. So I have to tie it up. So I have tensile stresses here. This distribution of stresses, what does it correspond to? It does correspond to a parasite bending moment. Let's call it M bar. On the bottom flange is exactly the opposite, because the two flanges tend to go in opposition of phases. So if you go on the bottom flange, I will draw it here. So this is the top flange, and this is the bottom flange. On the bottom flange is exactly the opposite. So you will have bending moment like this. The two bending moment, if the two flanges are equal, the two bending moment are equal and opposite. So if you look at the beam as a wall, it's under equilibrium because there are just two bending moments, but they do not alter the global equilibrium. But locally, something is happening. Okay, this bending moment is a parasite bending moment. It is not applied to the cross section. It's an effect of the restrained warping. It's maximum where the warping cannot occur, but if we consider this beam like a cantilever, it's maximum where the beam is framed into the wall or the support, and it's zero at the free edge, because at the free edge there is no bending moment. There cannot be anything. So there are these two bending moments, and their value changes along the axis of the beam. What does it mean that the bending moment changes along the axis of the beam? If there is a bending moment which is not constant, there is a shear force. There is a shear force. So what arises here, now let's use the purple, which is nicer. Red seems a mistake. What arises here is a couple of shear forces The shear forces are the results of the parasite bending moment, which is non-uniform along the axis of the beam. But those shear forces have a lever arm because they are not applied at the same level. They are applied in the two flanges. And you see that they form a torsion moment which is resisting the applied one, together with the usual blockage of the rotation. So, in cross sections that, as we say, are non-star cross sections, so they must not be solid cross section, and if they are made of thin walls, the thin walls must not converge in a unique point. We have seen in a slide yesterday. You must have thin walls, but they must be separate. There must be a lever arm effect. Because if you have a T cross section, you have this shear, but if you have a T cross section, you have the shear, surely. You have a shear in the flange, you have a shear in the web, but they do not form a torsion moment. They converge in a point. So you must have the geometry of the cross-section which leverages upon these parasite shear forces to exploit them as an additional contribution to torsion resistance. So there is this additional contribution which is called warping torsion or Vlasov torsion, as opposed to the main contribution, which is this one, which is the desenvenant or circulatory torsion. It's called Vlasov torsion because the first one to realize this was a Russian engineer, Vlasov. He was a railway engineer. Well, as a matter of fact, the shape of the railway is similar to I-beam and so on. But Vlasov was working on composite steel profiles where this aspect was very important. So, how can we quantify this warping torsion? Let's try to make a very simple model. There is a little math, but I try not to be complicated. So let's draw the cross section here. And let's say, okay, because of the torsion, the cross section rotates about its center of an angle phi. Okay? Then, let me put my glasses. Let's pick up this point here. Okay? This point here has ended up here. This point here ends up here. But if I look at this displacement here, u, just the horizontal part, because if I look at the flange from the top, what I do see is something like this. And I see this point ending up there. X-axis, this is Y, Z, X-axis is inside, yeah, because this is Y and Z. This, take it, displacement is in the direction of z-axis, okay? Take it there. Just abstract from the signs now. How can I express u? No. Angle phi times the, if this is the total depth of the cross section, h by 2. And as I said, there is a bending moment here, m. I can say that this m is equal to minus e. The moment, I'm just looking at the flange now, minus e, the moment of inertia of the flange, the second derivative of u. Consider this as a very thin beam, which behaves like a beam by itself, okay? So you consider each flange as a separate beam, and you write the equation of the beam for that. What we have said here, this torsion moment here, the Vlasov torsion T, you can express as V times H. This is V, and this is H. That's right, T Vlasov. Right? So how can I calculate V? Because this is what I need. I need T equal to V times H. So I need V. dm over dx. V is dm over dx. So is minus E j flange, the third derivative of u, but u is phi h half, is minus E j flange, the third derivative of phi, and I put some h half here. So this is an additional contribution to the torsion. So your equation becomes now T equal to gjt d phi over dx minus E j flange h half d3 phi over dx cubed. Well, if you are familiar a little, for example, if you are in work with steel structural elements, you have a catalog of the profiles. They are fixed, standardized shapes. And you pick up those catalogs and you find all the information that you need. And among this information, what you find these two cross-sectional characteristics. You find the two main moments of inertia. But you don't find this one, the moment of inertia of the flange. Well, you can say, no matter, I know how much wide is the flange, I know its thickness, I can calculate it easily. But you know, there is this other thing. Let's try to make this tutorial. I pick up a still profile, so not worry. Let me find some numbers here on my. Okay. Okay, this profile, now you have to pick up your calculator. This is 100 millimeters. This is, don't mind that it's still and not concrete, just to have the sensibility on the number. This is 5.6. This is 8.5. And the total depth is 200 millimeters, okay? Then I tell you JZZ is equal to and JYY according to yes, it's this. Okay? So you can see that the stiffness about this axis is about 14 times the stiffness about the other axis. Okay? But imagine this was something that my professor in concrete structural design used to tell me. So he said, imagine that you are in a resort, nice summer vacation, and you realize that the beam of your room does not convince you. You see a little bit, but you don't have the tables, the handbooks, and so on. But you can make, some hand measurements. So you realize that these dimensions here, okay? How would you, I'm asking you, how would you calculate JYY? This number here, 14, 24, and so on, it's something that I picked up from a handbook. And it takes into account also the fact that actually, for example, here you have some rounded corners, so that the shape is not exactly 3 rectangles. But imagine that you are able to sketch out 3 rectangles. How do you calculate the moment of inertia of this cross-section about this axis here? Try to do and see what do you get.